Okay, today we're going to look at Y13 Pure Trig, something what I call the Rcos theta plus alpha form. This is actually one of the easier parts of this trig chapter because more often than not, the setups like this, they'll give you a function like this, and in this case 3 cos theta plus 4 sine theta, and they'll tell you what form they want it written in. And therefore it becomes quite routine. The questions don't change a great deal into what they ask you to do. There might be the odd little twist and turn, but the majority of it is comparatively routine. Things to be aware of: they should normally give you the form that you wanted in. If they don't, you just need to choose one of the sine of a sum, sine of a difference, cos of a sum, cos of a difference that has the correct plus or minus in the middle. So in this case, because it's a plus, we're looking at cos of a difference. We could have written it as sine of a sum, and there would have been a slight difference in how the answer looks. So let's have a see how we're going to do this then. First thing I'm going to do, underneath the function here, I'm going to rewrite the form that they want it and expand it. I'm basically looking to match coefficients, so I'm going to write the r cos theta minus alpha there, and it equals r cos theta cos alpha plus r sine theta sine alpha. And the idea is that the bits with the cos theta should match up. So it's telling me that r cos alpha must equal 3. The 3 that's there, 3 times cos theta, well, I've got r and cos alpha times cos theta there. And similarly for the other term, the sine theta matches up as well, so that r sine alpha must equal 4. So I'm going to write r sine alpha there. You'll see why in a moment. And that's matching up. R sine alpha is that, r cos alpha is this one. And I've got enough information there to quickly calculate what r is and quickly calculate what alpha is. And that's the standards for the start of this question here. How do I get alpha? Oh, divide sine over cos, because the r cancels out, and that leaves me with tan alpha, which is 4/3. Quick pressing of buttons, it was in degrees, so alpha is inverse tan of 4/3, 53.1 degrees. How do you find r? Well, in reality what we have is this. If that's alpha and that's r, this is r sine alpha, which equals 4. Oops. Put the r there. And then on the bottom we've got r cos alpha, which is 3. Right angle triangle, and it's Pythagoras basically using the 4 and the 3. So r equals the root of 3 squared plus 4 squared, which is 5. So, to sum up, how do you find the r value in this form? Do Pythagoras on the two numbers that you've got there. How do you find alpha? Divide the two values you've got, and then do the inverse tan. The only way you can go wrong, therefore, is have these two numbers the wrong way round, and what you were finding, therefore, is that angle there, rather than the alpha that you want here. And that's really it. As long as you take time to match up the coefficients, to show to yourself which one is r cos alpha, which one is r sine alpha, and they give you the r sine over the r cos, so it's that way around. That's it. As long as you do that little step there, I don't think you can really go wrong. The little twists and turns might be, occasionally, they'll write these two, especially when it's plus, the other way around. So don't just think when we expand this one as r cos cos and r sine sine, if they've written it as 4 sine plus 3 cos, don't just go, oh, r cos is the first number there. It has to match up with the cos and the cos there like that. So r cos alpha is 3 in this case, and r sine alpha is 4. Okay, we'll look at the second example, exactly the same sort of thing. There's our setup here. 4 sine theta plus 2 cos theta like this equals, and they want it in the form r sine theta plus alpha. The only slight twist is we're going to be in radians. I'll need the calculator for this. I knew 4/3 is a fairly standard one there. I knew the answer to that one. I'll need the calculator for this one. So, as before, it's plus, so I've got sine of a sum, that's using the plus, but I will write r sine theta plus alpha equals r sine theta cos alpha, so it means that r cos alpha is 4, and then plus r cos theta sine alpha. And I've written it that way around to get that. So I've got r cos alpha equals 4, and r sine alpha equals 2. Divide them, 2 over 4 is a half, tan alpha. Oh, I'm thinking then it was a standard one, but it's tan, not sine. So tan alpha is a half. So alpha is, first thing we're going to do is make sure I'm in radians, so angle, radians there, and then do shift, tan 0.5 equals, and we'll round off a little bit, 0.46 radians. Okay, that's my alpha value there. And then r is Pythagoras, root 2 squared plus 4 squared equals root 20. I wouldn't leave it as root 20, I'd take 4 out, and 2 root 5. Like that. So how I should have done it for the one before, so I can write, if I wanted a final answer, really, I should have really gone like this, equals 2 root 5 sine theta plus 0.46 radians. And there we go, that's my rewritten version. Now we're going to look, and I'll do a quick rub out of this because I'll need this board in a moment as well. We're going to look at how your exam question is going to look. That's really the start of this question here. This is now your typical A-level question. Here's a function, fx equals 8 cos x minus 15 sin x. You want it written in the form r cos x plus alpha, so I'm going to do my expansion. We're going to use it to do things with it. So I'll do the first part as normal. So I'm going to expand it because of the sum. So r cos x cos alpha minus r sin x sin alpha. And as before, the cos x's match up. So I've got r cos alpha equals 8. And then r sin alpha is the other value, 15. Notice, because you choose the correct version with the correct plus or minus sign, these values here should always be positive. And then when you're doing your tan alpha, you should always be getting an acute value. So that's why they ask for alpha between 0 and 90 degrees in this case, or alpha between 0 and pi over 2. So that's my tan alpha then. So alpha is the inverse tan of 15 over 8, not a standard one. Yet again, change back to degrees. And then shift tan 15 divided by 8, close bracket, equals 61.9 degrees. 61.9 degrees. And r by Pythagoras is root 8 squared plus 15 squared, which is 17. So I can rewrite it then as 17 cos x plus 61.9 degrees. Why do I do it? Well, it helps me solve equations. Because at that stage there, if I was to solve fx equals 10, 8 cos x minus 15 sin x equals 10, I've got x appearing twice, and that's no good to me. What I want to do with it is to be able to rewrite it as 17 cos x plus 61.9 degrees equals 10, and undo it. Because x appears once and once only, I can then solve it by undoing. What am I doing to x at the moment? I'm adding 61.9, I'm doing cos of it, I'm times by 17, it gets 10. So how do we then undo it? Divide by 17, do the inverse cos, and minus 61.9. And that's pretty much it. So I can say that x plus 61.9 equals shift cos 10 over 17, which will equal whatever it does. Shift cos 10 divided by 17, still in degrees, and it gives me a nice one there, 54.0 to be honest. I'll round off. Now, what I should have done as well, because this, when I subtract the 61.9, it's going to be out of my range. I should have thought about x plus 61.9 being somewhere between 61.9 and 421.9. The calculated answer gives me a value that's not in that range at all. So to get my two solutions, 0 to 360, I can do what I do normally. How do I find a second one, 0 to 360 from this? Take this off 360 for cos. So I'll get 306.0 degrees. And then I can undo that. But I also need to add 360 onto this one to get 414.0 as well, because that's going to give me my answer that's in the range. So because this one here isn't going to help me get an answer that's in x is 0 to 360. It helps generate these other two, but that's it. And now x, take off 61.9, so I'm feeling very lazy today. 306 minus 61.9 equals 244.1, and 414 minus 61.9 equals 352.1. And there's my two solutions. And as I say, I've been able to do it because I've rewritten the function so that x appears once and once only. The other things they tend to ask us to do with it is find the maximum and minimum values for these functions and the smallest x values that give us these maximum and minimum values, and then put it all together, sketch it. Once I know that it crosses the x-axis here and here, I can say where it crosses the y-axis by sticking x equals 0 in, basically, and solving that one. I can then go on and do all sorts of things with it here. So this wasn't, sorry, where it crossed the axis and where it crossed 10. But I can begin to use the maximum minimum to sketch thing as well. So let's have a look now. I know that a general cos curve starts like that. It has the maximum here when the bracket, the x value as it were, is equal to 0. So, or 360. So I can solve x plus 61.9 degrees equals 0 or 360. Now obviously taking 61.9 off, that's no good to me, but taking that off there will give me x equals 298.1, and that's where it tops out. That's the maximum value there. The minimum value is when x plus 61.9 degrees equals 180. So take that, x equals 118.1. Because of the way the thing has been written as 17 cos x plus 61.9 degrees, that 17 is the maximum and the minimum value of the function. So when it's at the maximum, it'll be 17, and when it's at the minimum, it'll be minus 17. Because now rewritten as one function, I know that what does the 61.9 do to the cos curve? It shoves it, because it's in the brackets, backwards, 61.9. What does that 17 do to the cos curve outside it? It stretches it by a function of 17. So I can begin to think about that sketch there. I can begin to think about the same sketch here, doing a bit more. That will be at minus 61.9 there. Everything's been shoved back 61.9 degrees, and then times it by 17. I can then begin to think about my shape of it like this, and there, that's 0 to 360, and then carrying on if necessary like that, and hopefully I can begin to think about the sketching of it. That's at 118.1 minus 17. That one there is at 298.1 plus 17, and it crosses when x is 0 at 17 cos 61.9. 17 cos 61.9. Hopefully it should be something, it should be fairly obvious when I think about it. Probably like 8. And you could have done that by sticking x as 0 into the original function. I could solve these points, stick y equals 0, and solve cos x plus 61.9 equals 0. I know that all this is, because I've shoved everything back by 61.9, it would have crossed at 90. 90 minus 61.9 is 28.1, and it would have crossed at 270, and that point there is 270 minus 61.9, which is 208.1. Everything therefore has gone up 90 degrees, from there to there to there to there. Okay, so I've got all the information that I need. I can tell where it's crossing the axes, where it's crossing the y-axis, where it bottoms out there, where it tops out there. It matches up everything, and that will be worth a lot of marks. So to sum up then, why do we do this? We want x appearing once and once only. Why? Because we can then solve equations easily. We can then think about how to get the maximum, which is generally r, and think if it's cos or sine, how do you get the maximum value for cos when it's at the top there? Sine, same deal, but different shape, different points on the curve, and its minimum when it's at the bottom there. Why do you get cos equals to -1 when the bracket in this case is 180? Solve that. There's my answer.